Welcome to lecture 21 of my series on classical thermodynamics. In the last lecture, we had looked at some applications of the second law which brought home the important role which the potentials played. Remember, a thermodynamic potential, is really very important because it contains complete thermodynamic information about a system. So if you're talking about a simple hydrodynamic system, simple meaning with a single component and only one means of doing work, in this case that means we have taken to be hydrostatic by changing volume. Then if you know the internal energy as a function of entropy, volume and number of moles, you have complete thermodynamic information. Of course, you can turn this around and say, if you know entropy as a function of U, V and N, you know the complete story about this particular system. What is important is that the other thermodynamic potentials can also contain complete thermodynamic information. So if you express the enthalpy of the system, H, U plus PV, as a function of entropy, pressure and number of moles, or the Helmholtz free energy F as a function of temperature, volume and number of moles, or the Gibbs free energy G as a function of temperature, pressure and number of moles, then any one of these can give you complete thermodynamic information. Now in the last lecture, we looked specifically at how systems evolve and how do we know that they have reached equilibrium. To remind you, a closed system at a fixed energy and volume, closed here means number of particles or number of atoms, amount of particles will not change. A closed system at fixed energy and volume can only evolve towards increasing entropy. This is the famous statement by Clausius that the entropy of the universe only increases. So when is equilibrium reached? Equilibrium is reached at a maximum of entropy. So once the entropy of the universe reaches a maximum, what we will have is what is called the heat death of the universe. Nothing will evolve any further. If you don't think about the universe as a whole, but just think of a system which cannot exchange heat with its surroundings, being enclosed in an adiabatic wall, has rigid, immovable walls so that it cannot change its volume, and impermeable wall at the same time so that the number of particles inside cannot change, cannot either increase or decrease, then the equilibrium for that system will be reached when it reaches a maximum of its entropy. Now, very similarly, but with slightly different conditions, we find the following. A closed system at fixed temperature and volume can only evolve towards lower and lower Helmholtz free energies. So equilibrium is reached for such a system when the Helmholtz free energy reaches a minimum. On the other hand, a closed system at a fixed temperature and pressure, note the difference, this one is at fixed pressure, evolves towards lower Gibbs free energy only. And that means that equilibrium will be reached once the system reaches the minimum possible value for G. Of course, minimum possible value for G given that temperature, that pressure and that number of or amount of particles. Now, we ended the last lecture with this puzzle. If this entropy, which is a function of U, V and N, S of U, V, N completely determines the system, as we have just been saying, then how can a system at fixed U, V and N even evolve? The question of how it reaches a maximum of S simply doesn't arise because once you fix the U, the V and the N, there is only one state for such a system. I admit that this actually gave me quite some time to grasp when I first learned about this, But this is really rather simple. The whole issue is the system that we are dealing with, is it really a simple system? If we are talking of the universe as a whole, of course it is not a simple system. Remember, a simple system can be described by just three parameters, u, v and n. Now it's true that for the universe or for any sufficiently well-shielded system, u, v and n will be perfectly well defined and fixed. But those are not enough to describe the state of the system completely. After all, the universe will be made out of many subparts, and you would need to know parameters corresponding to the different parts in order to know what its state is like. So, overall energy, overall volume, overall amount of particles being determined does not tell you that the system cannot change any further. And the same goes for the other thermodynamic potentials. So I'm going to illustrate this today by one of the simplest possible non-simple systems, which we are going to discuss next. Now, if you go simply by the number of parameters needed to describe the system, then the simplest non-simple system would perhaps be a system with two components, like say a mixture of sugar and salt, or even better, a solution of salt and water. Then, of course, in order to describe the thermodynamics of the system properly, you will have to describe the total energy, the volume, the amount of the first component, maybe the salt, and that of the second component, maybe water. However, it will be easier for us to discuss this whole scenario if we think of two simple systems somehow put together as our almost simple but not quite simple system. So let us try to understand what we are talking about. Basically, we are talking about a situation where we have two systems, maybe two gases, not necessarily ideal or not even necessarily gases, but okay to think of them as gases, confined to two regions of this whole enclosure. The two are divided into two regions by a partition in between. And if we assume that the partition is adiabatic, immovable and impermeable, then the number of atoms on either side cannot change. Neither can the volume of each side, and nor can the energy of each side, because, well, that's not quite right. We would also, but we are assuming that the wall is adiabatic. So, since there is no heat flow possible and no work possible, with the wall being immobile, the energy of both sides will also be fixed. So, the gas on the two sides, I'm going to keep on saying gas just for completeness, the gases can be in perfectly good equilibrium with their parameters being completely disconnected from each other. So on the left hand side you have this gas 1 with internal energy U1, volume V1, number of moles N1. On the right side you have S2, the entropy, which is a function of U2, V2 and N2. Now the overall system is enclosed in a wall surrounding it, and that wall happens to be adiabatic, immovable and impermeable. So right now both the outside wall and the partition in between are adiabatic, immovable and impermeable. Now, no matter what this partition is like, because the outer wall is adiabatic, immovable and impermeable, N1 plus N2, the total amount of atoms or amount of material in the two chambers put together, that's fixed. So N1 plus N2 is equal to a fixed number N. Since the overall boundary is immovable and so its volume cannot change, V1 plus V2, V, which is the net volume of the two systems, is also. And because the overall system is adiabatic on top of being immovable, the wall of the overall system, that is, and impermeable, U, the total energy U1 plus U2 is also fixed. Now what is the entropy of the entire system? S is S1 of U1 V1 N1 plus S2 of U2 V2 N2. Now here note that U1, V1 and N1 are fixed to begin with, assuming the partition in between is really adiabatic, immovable and impermeable, and so is S2. So S1 and S2 are fixed quantities because the states on the two sides are already fixed by their respective parameters, U1, V1, N1 and U2, V2, N2. And the entropy of the whole system happens to be just the sum of these. Now the question we will have for you, or the question that we are going to discuss, is what happens when you relax these properties for the intermediate wall. We will still assume that the overall outside wall is adiabatic, immovable and impermeable, but the partition in the middle, suppose, is now changed to something which is not adiabatic, diathermal, something which can move, flexible, and something which is permeable, allows atoms of either kind to travel from one side to the other. Now note that even under such a situation, once equilibrium is reached, you will get well-defined U1, V1, N1 and U2, V2, N2. And then the entropy of the whole system will be this, S1 of U1, V1, N1 plus S2 of U2, V2, N2. And U1, V1, N1 and U2, V2, N2 will still obey these equations. The net energy, net volume, net number of particles will stay the same. The question that we are going to ask is, can such a system evolve? The answer is, of course it can. Although U cannot change, U1 can. So can V1. So can N1. Of course, if U1 increases, U2 must decrease by the same amount. Similarly, if V2 rises, V1 must go down by the same amount, and so on, just to maintain these three conditions. So let's just ask ourselves first, how much will the entropy change when I make a slight change in the parameters? So U1 changes to U1 plus dU1, V1 changes to V1 plus dV1 and so on. And it's a matter of simple calculus of multiple variables to work this out. But let me just point out that we can actually cut through a bit of the partial derivative simply by noting that du is given by TdS minus PdV plus mu dN. This is something you already know. And this can be solved immediately to give us ds, which is 1 over T du plus P over T dV minus mu over T dN. We are going to use this. This is for a simple system. What we have is a sum of two simple systems. And this formula will help us to find out how much its change in entropy is going to be. So as the partition is relaxed, the relaxation can be in many ways. For the time being, I am allowing it to relax in any way, which means U1, V1, N1, all three are allowed to change. Then ds, the change in the entropy of the system, will be ds1 plus ds2. Now ds1, of course, these are the partial derivatives involved. You can write them, or you can simply use the formula that I've just written down a while ago. ds is 1 by T du plus P by T dV minus mu by T dN, and see that this expression that we have write down here is just the entropy change of the first system, ds1. And we have an exactly similar statement for the entropy change of the second system. 1 by T2 du2 plus P by T2, that is P2 by T2 dV2 minus mu2 by T2 dN2. Now the important point is we still have to keep in mind that our constraints are still in place. U1 has been allowed to change, but U has not been. So U1 plus U2 is fixed. And that means that dU2 has to be minus dU1. Similarly, this dV2 is negative of dV1, the dN2 is negative of dN1. And that means that we can take them together and collect them together in this particular form. ds, the entropy change of the whole system, is 1 over T1 minus 1 over T2 du1 plus P1 over T1 minus P2 over T2 dv1 again minus mu1 by T1 minus mu2 by T2 dn1. I have eliminated each one of the changes in the second system in favor of the change in the first one. That's just a choice I have made. You could have written everything in terms of the second system's parameters as well. That would have changed the expression slightly, but would not change any of the conclusions we are going to draw. So now that we have an expression for the entropy change of our non-simple system, let us see what this tells us about equilibrium of this system. Now for this, we are going to take a look at different configurations for the wall in between. Remember, this expression has been derived assuming u1, v1 and n1 can all vary. Now in what follows, I may sometimes refer to a wall or to a partition. Note that in both cases I will be referring basically to the partition in between the two subsystems, this wall in between, not the overall outer wall. That is not going to be changed in any way. It's going to stay, as I've repeated over and over again, adiabatic, impermeable and immovable. Now let's start with relaxing just a little bit of the restraints on the partition. We started out, as we said, with a partition wall which is also adiabatic, immovable and impermeable. But let's just say our wall now becomes adiabatic, becomes non-adiabatic and still maintains the other two conditions. So what we are talking about is a wall which is diathermal, rigid and impermeable. Rigid is of course another way of saying immovable. So dv1 and dn1 are still 0. The du1 and of course du2 can change because heat can flow across the partition from one side to the other, changing the internal energy of this side at the expense of the other side. Now note that ds has a much simpler expression. This term and this term drops off because dv1 and dn1 are 0, and so we are left with 1 over T1 minus 1 over T2 du1. Now note that we have already said that entropy can only increase, and that means that if T1 is greater than T2, of course the left hand side of our picture is at higher temperature, then this thing in the bracket here, 1 over T1 minus 1 over T2, is negative, and so ds being positive would mean du1 has to be negative. So energy, in this case heat, can only flow out from the higher temperature and into the lower temperature, not the other way around. Of course, this conclusion is something which should not come as a surprise to any of us. But it's good to see that our version of the second law of thermodynamics actually tells us this. Now what about thermal equilibrium? Now equilibrium will be reached only when entropy reaches a maximum, that is ds reaches 0. Now since du1 is allowed to change, the wall being diathermal, the only way this can be maintained is if T1 is the same as T2. So we have figured out that this system will evolve only towards equality of temperature. Heat can only flow from a higher to a lower temperature. And finally, equilibrium will be reached. This is of course thermal equilibrium only when T1 equals T2. No surprises here, but it's gratifying to see that our more advanced conclusion based on complex system thermodynamics gives us back results which we know and hopefully trust. Now, what happens if the wall happens to be diathermal and movable? Let's keep the impermeability in for the time. Now, in this case, what happens is, of course, dV1 can change and du1 can change also. Now, you might say that since the wall is moving, some amount of work is being done, so that will contribute to du1, and you will be perfectly right. But there will be other contribution to du1 as well, a contribution which comes from heat flow. So, basically dV1 and du1 will change independently of each other. In this case, ds of course has these two terms. The minus mu1 by t1 minus mu2 by t2 into dn1 term, that's dropped off. But now, because we are dealing with a situation where at least in equilibrium v1 can change and so can u1, the only way this is to stay at 0 is that if this bracket vanishes, and so does this bracket. Now, vanishing of this first bracket tells you T1 equals T2 as before, and then when we apply it to this bracket vanishing, you get P1 equals P2. So, if you have a wall in between two subsystems, which is diathermal and flexible, then the pressures on the two sides have to be equal. That's mechanical equilibrium. The temperatures of the two sides would have to be equal. That's thermal equilibrium. Now, what about if the wall were rigid but permeable? That is, allowed material to flow from one side to another through, say, pores in the wall. And the wall is still diathermal. So now U1 can change, so can N1. V1 cannot change. dV1 and dV2 are both 0. So our master expression now becomes this. And now again, if we want to look at equilibrium, we are going to get T1 equals T2 from the vanishing of this bracket. And since this bracket will also have to vanish independently, you must have mu1 by T1 equals mu2 by T2. But since we already know T1 equals T2, this tells you mu1 equals mu2. Now this actually brings home to us the importance of the chemical potential. It actually tells you under what conditions you are going to get chemical equilibrium. Mu1 would have to be equal to mu2. The two chemical potentials would have to be equal if the two systems are in equilibrium despite being separated by a wall which is permeable. Now finally, let us try relaxing all the properties. Diathermal, movable and permeable wall. Of course, for that, the expression for ds will be the whole thing here. Now, if you want this to vanish at the equilibrium state, no matter what change in U1, V1 and N1 you carry out, note that now that you have reached an equilibrium state, U1, U2, V1, V2 and N1, N2 will have settled down to their equilibrium values, but it's not impossible to conceive of a means by which you can change them. The only thing you cannot change is U1 plus U2, V1 plus V2 and N1 plus N2. So, if you want to keep S a maximum at equilibrium, what you have to ensure is that when you change U1, V1 and N1 independently of each other, then this ds still vanishes, and that means each of these coefficient brackets have to vanish. T1 equals T2 will follow from this one. The second coefficient bracket will tell you P1 has to be equal to P2. The third one will tell you mu1 would have to be equal to mu2. So, T1 equal to T2, thermal equilibrium. P1 equals P2, mechanical equilibrium. Mu1 equals mu2, chemical equilibrium. Under such a condition, the two subsystems, part 1 and part 2, are in true thermodynamic equilibrium with each other. Same temperature, same pressure, and same chemical potential. So, thermal, mechanical, and chemical equilibrium all together. Now this, of course, was pretty old stuff. It's nothing new. Indeed, we nearly started our discussion with what is equilibrium and what are different kinds of equilibrium, and there we defined all of this. Here we are actually writing down conditions for those equilibriums. Now, simple though these conditions might seem to be, and familiar ones of course, let me stress that these are actually purely formal. What I mean by this is that for a given system or given pair of systems 1 and 2, these equations, while they sound obvious, would actually be possibly complicated sets of equations. T1, which is a function of u1, v1, n1, will be equal to T2, a function of u2, v2, n2. And similarly, P1 and P2 being equal could mean some complicated function of u1, v1, n1 being equal to some other complicated function of u2, v2, and n2. The same goes for mu. So despite the apparent simplicity of these conditions, there may be some surprises hidden in them. Now, just to illustrate what I mean here, I will start with a very, very simple situation. So we will consider a situation where both halves of my complicated system is made of the same material, obeys the same fundamental equation, and this is the equation that we are going to take for both halves. U1 will be A times N1 to the power 5 by 3 divided by V1 to the 2 by 3, exponential of twice S1 by 3 N1R. U2 will be given by a similar expression with N2 V2 S2 replacing N1 V1 S1. Now this should not be a very unfamiliar expression. In an earlier lecture we had shown that this is exactly the fundamental equation or the equation which contains complete thermodynamic information about a monoatomic ideal gas. Now, the form in which we need this equation here is the form which expresses entropy as a function of internal energy, number and volume, and that's pretty straightforward. You just solve this to find S is 3nR by 2 log u v to the 2 by 3 by a n to the 5 by 3. Here a is just a constant, which will not really play much of a role in what we are going to talk about. Now, from this expression of S, we can easily figure out expressions for temperature. These expressions are valid for each half of my complex system. 1 over T can be easily seen to be 3nR by twice U. P over T, which is minus del S del V, will work out to be 3 by 2 nR into 2/3 V, which simplifies to nR over V, and mu over T will work out to be something slightly more complicated, an expression which looks like this. Now, armed with this, let us try to understand the situation that will happen when you have a system made out of two ideal gases on two halves separated by a wall, and that wall can be of different kinds. So let's start with this basic premise. We know the initial equilibrium states of the two systems, subsystems, the two ideal gases, Ui, Vi, Ni1 and Ui2, Vi2, Ni2. And thus we know the total energy U, which is the sum of Ui1 and Ui2, total volume V, total number N. Now, under this situation, what happens if the wall in between, which began as an adiabatic rigid impermeable wall, is made diathermal? Let's start with that. If the wall becomes diathermal, but still stays rigid and impermeable, Vfi, the final volume, where I is 1 or 2, will not change, will stay Vi. So Vf1 is Vi1 and Vf2 is Vi2. Similarly, Nf1 is Ni1, Nf2 is Ni2. The numbers and volume on either side do not change. Now we need to determine Uf1 and Uf2. How much is the energy on the left hand side and the right hand side finally? Remember, the wall is now diathermal, so energy can be exchanged via the wall. in the form of heat. Now thermal equilibrium demands that 1 over T1 has to be equal to 1 over T2 finally. That is, this is the final temperature, Tf. 1 over Tf is equal to these two quantities. Now Tf, remember, we had already worked out for the ideal gas has to be 2/3 U by Nr. So UF1 by NF1 has to be equal to UF2 by NF2. And of course, this immediately can be simplified by using addendo. So this is the same as 2 over 3R UF1 plus UF2 by NF1 plus NF2. And we know what these things are from the initial conditions. This is the total energy, sum of the two internal energies on the two sides, and this is the total number or amount of material. So 2/3 U by Nr. That's the final temperature. So given the initial conditions, where I know capital U and I know capital N, I can find out the final temperature. Of course, now that I have found out the final temperature, finding out the final energies on the two sides is also pretty straightforward. In fact, you don't even have to go back to the full expression. You just use this ratio, which we have just derived right now, and that actually tells you that UF1 has to be Ni1 by N into U, and UF2 has to be Ni2 by N into U. So the energies get distributed in the ratio of the numbers. Remember, the numbers are whatever the numbers were initially, they don't change. So what we have done here is written this for the final temperature equality, but then replace the NF1 and NF2 by Ni1 and Ni2 to get to this expression. So this was pretty straightforward. If the wall is made diathermal, of course, still rigid and impermeable, the volumes don't change, the numbers don't change, the energy gets redistributed in proportion to the number of particles or amount of the gases in moles, and the final temperature can be easily worked out from the total energy and the total number. Now what if the wall was movable and diathermal? Then the only constraint that remains is that of impermeability. So the final number and the initial number, or final amount and the initial amount of the material on both sides will stay the same. So NF1 is equal to Ni1 and NF2 is equal to Ni2. Thermal equilibrium, of course, will tell you that 1 by T1 and 1 by T2 are equal and they're equal to 1 over Tf. Gives you exactly the same expression as before. Tf works out to 2/3 total energy by Nr in exactly the same manner. So the final energies are redistributed in the ratio of the numbers, which, let me remind you once again, does not change in the process. Now what about mechanical equilibrium? Mechanical equilibrium will tell you that once equilibrium sets in, pressure on the left by the temperature on the left is equal to pressure on the right by the temperature on the right. That's the same as Pf by Tf. Now Pf by Tf, we had already worked out, is R Nf by Vf, and that's Nf1 by Vf1 and also Nf2 by Vf2. And again, using addendo, this ratio is the same as R times capital N by V, capital N being the total number of moles and capital V being the total volume. So final pressure is simply given by this times Tf, and by putting back the value of Tf, we can get Pf is 2/3 U by V. Now this again should not come as a surprise. This is exactly what the pressure of an ideal gas is. Now that both sides of the system are the same pressure, that pressure is given by 2/3 of total energy by total volume. Note that in this case, final pressure are equal on the two sides, final temperatures are equal on the two sides, and the energy is distributed in the ratio of the numbers, and you can also check easily that this means that the volumes are also distributed in the same ratio as the numbers. The wall being impermeable, the numbers are whatever they were to begin with, So in this case also it's easy to figure out exactly how much energy will be there on each side and how much volume will the gas have on each side. Now let us turn to the final situation, or the final one that we are going to discuss right now. A wall which is diathermal, flexible and permeable. So this of course will be a situation where thermal equilibrium will be there, so will mechanical equilibrium. And so the previous considerations that we have already discussed will again work out. But what about chemical equilibrium? Chemical equilibrium will demand that on the two sides mu by T will be equal and will be equal to mu F by Tf. And by plugging in the values, you get this equality. These two expressions, which are both expressions for mu by T, but this one is of course for system 1 and this is for system 2, would have to be equal to each other. Note that we already have UF1 by NF1 equals U by N, and similar expression for 2 actually, and VF1 by NF1 also is capital V by capital N. These follows from the thermal and mechanical equilibria respectively, and exactly identical expressions work for the second system as well. This will immediately tell us that these two expressions are actually identical without imposing any further condition. And they're actually equal to this expression. So if you know the initial total energy, initial total volume, initial total number of moles, you know the final mu. After all, you know mu F by Tf, and of course we have already figured out what Tf is. By multiplying by Tf, we find this is the expression for the final chemical potential on both sides. So even when the wall is diathermal, flexible and permeable, you can figure out the final pressure, the final temperature and the final chemical potential. However, you have to be a bit careful in this case. What you cannot find out is what will the final volume, final number of particles, final energy on both sides be. That might come as a surprise, but if you look at the conditions, all you get is this result, that finally, once equilibrium is reached, these quantities on the left hand side must bear the same ratio as the corresponding quantities on the right hand side. But what exactly will the values be, that is not determined by the initial conditions. So you see that even in such a simple situation where you have two gases on two sides with a permeable, flexible and diathermal wall, the final situation cannot be determined by thermodynamics alone. It will be determined by other factors, like how much is the friction between the movable wall and the rest of the container. What is the rate at which the various components diffuse and so on. Thermodynamics alone cannot give you a complete solution to this problem. This might actually come as quite a surprise because this is a very simple situation. Just two ideal gases on two halves of container. But even there, the problem is actually not completely determinate. Now we will end with another situation where things are even more indeterminate. And while the results that we have been talking about over the last few minutes have been specific to ideal gases, this indeterminacy that we are going to talk about next is a general one, which will occur whenever you have a wall which is of a kind we had not considered so far. A wall which is adiabatic and flexible. So let's see what that kind of a wall tells us about the final equilibrium situation. So here we have a situation like this. This wall is movable, so it can move finally from here to here. And in the process, the internal energy has changed from U1 to U1 plus dU1 on the left. This has become V1 plus dV1 starting from V1. And of course, similar changes have taken place on the other side. We are assuming the wall is impermeable, so N1 stays the same on both sides. Doesn't change. N1 stays N1, N2 stays N2. Of course, dV1 plus dV2 is 0 in this case. But now, because the wall is adiabatic, there is no heat transfer. The change in internal energy is only due to the work done. Now, this is where things get a bit complicated. How much work is done on this gas when this wall moves? Note that what does the work is the force exerted by the other half, not this one. So even if we assume that the wall is frictionless, the force will be given essentially by the pressure on this side. So when the volume expands by V1, the internal energy changes. In fact, it has to push against the external work. The internal energy changes. This is a mistake. This should be dV1. The volume changes by dV1, but the pressure outside is actually given by P2, the pressure exerted by the second thing. Note that the pressure exerted by this gas here times the cross-sectional area is the force which is acting on this gas, or rather on the wall, as the wall moves, and that is changing the internal energy of the gas inside. That's the work done on the gas on the left. Well, very similarly, dU2, the internal energy change of second part will be minus P1, pressure exerted by the left, times dV2. Of course, they're the same as plus P1 dV1 from this condition. Now, there is a puzzle for you right now. Initially, the two pressures, P1 and P2, will definitely not be the same. So, what you can see here is dU1 and dU2 will not be negatives of each other. So, isn't this inconsistent with our statement that the overall system is enclosed? So, U1 plus U2 is constant. Well, actually it is. But let me point out that the theory that we have been developing is for equilibrium thermodynamics. And so even when the system changes state, the theory will be strictly valid only when the system changes very, very slowly, so that you're always very, very close to equilibrium. Quasi-static changes only. Now, if P1 and P2 were different from each other, then the wall would definitely jump and you would not really have a quasi-static change. And therefore, until the equilibrium state is reached again, you are not really in a position to say U1 plus U2 is a constant, because you are not even in a position to talk about U1 and U2, which are equilibrium concepts. So having said that, in equilibrium, what happens is simply this. ds now will be given by, as before, 1 over T1 du1 plus P1 by T1 dV1. This is the entropy change of the system 1, plus a similar expression for the system 2. But now that we put in, instead of du1 minus P2 dV1, and instead of du2 plus P1 dV1, and carry out the same calculation, of course remembering to change the dV2 here to minus dV1, so that everything here is in terms of dV1, note that this is what comes out of ds. So at equilibrium, what we will have is this ds has to vanish as volume changes, but now the internal energy change is no longer independent. It has been subsumed inside the whole expression. And when dV1 is not 0, but you still demand ds is 0, what you get is P1 equals P2. So, if you have a wall which is adiabatic but flexible, you again get something which is pretty straightforward. The pressures on the two sides must match for equilibrium. That seems quite obvious because unless the pressures matched, there would be an unbalanced force on the movable wall which will then move. However, notice that now you have no way of talking about any other parameter. What about the temperature? The two temperatures do not have to be equal at all for equilibrium. ds can be 0 for arbitrary change in volume, no matter what T1 and T2 are. So the final temperatures on the two sides cannot be determined from conditions of equilibrium. Of course, if you do not know the final temperatures, you do not know the final energies. Of course, you know the final number because that can't change from the initial value. From P1 equal to P2, what you will get is U by V. Ratio is given. In fact, you cannot figure out the final energy, neither can you figure out the final volume from here. Once again, this is something which cannot be figured out just from thermodynamics. It will have to depend on the kinetics of the situation. Note that there will be some friction in the walls, and that friction will determine the rate at which the wall can move. In fact, if you think about it, if there were no friction in the walls, then the equilibrium state will never be reached because the wall will keep on oscillating. Given that in a real wall there will be some friction no matter how small, ultimately equilibrium will be reached when the two pressures balance. But exactly where will the equilibrium be reached? What will the final volume be? What will the final temperature and internal energy be? That will all depend on how much friction there is in the wall, how massive the wall is, and other dynamical considerations which are not part of thermodynamics. I hope I have been able to convince yourselves that even this very simple system can lead to rather deep and complicated factors to worry about. In the next lecture, we will see how the equilibrium condition in terms of constant temperature and pressure, the condition that gives free energy reaches a minimum, will allow us to reach important conclusions about phase equilibria or chemical equilibrium. Bye till then.